All right, we want to learn how to add vectors up, or add force vectors specifically today. So I'm going to start out with the first part of this problem filled in. We've got an interaction diagram showing our blocking sled interacting with the player who's exerting a normal force on the sled. The ground, which is exerting a normal force due to the compression of the atoms in the ground. We've got the ground also exerting a friction force because the atoms in the ground are being sheared by the sled. And we've got a gravitational force because we're near the planet Earth. Quick qualitative motion map shows that, as the problem is asked us, that this object has a constant speed of 2 meters per second. If I want to add in some times here, I can add in some more information onto this graph and make it a little more quantitative. Okay, our qualitatively correct sketch of the free body diagram, that is, forces that look like they might be equal are equal. I'm going to alter this drawing just a little because I know the gravitational force is bigger than the force that the player is pushing with. We're given the player is pushing with a force of 100 newtons, right? And that's the only force we know straight up. We're going to have to calculate some other forces. And let's go ahead and calculate the other ones we have. Most obviously, we have a way of calculating the gravitational force of the Earth on the sled. Notice that I've just to be complete, I've put these extra subscripts down here. This is the normal force of the ground on the sled as opposed to the normal force of the player on the sled. Okay, so we can calculate the gravitational force. I'm going to write that here. Gravitational force is G times M. That's what we found in our experiments in the lab. We found G has a value of roughly 10 newtons per kilogram here at the surface of the Earth. The sled has a mass of 25 kilograms, so that gives us a gravitational force of 250 newtons. So I can put this down here too. So now those are the two forces that I know for certain. Now we can make some deductions about these other forces based on the fact that the free body diagram is balanced because we are moving at a constant speed. Okay? Well, I'm going to hold off on that right now. What we do next is to draw a scale drawing of the free body diagram, so I have to determine what kind of scale I want to use. I'm going to, let's see, what if I made every centimeter equal to 100 newtons? That means I would have to make the gravitational force 2.5 centimeters long, and let's see what that would look like. Yeah, that looks like it'll work. Let's try it. So I'm going to draw a force here, an arrow here that's 2.5 centimeters long. I'm going to be very careful to really make it 2.5 and not 2.6 or 2.4. And that's our gravitational force. Okay, and that means the normal force of the player on the sled is going to be, what, 1 centimeter, right? So here, let me just put this in here to remind myself. 1 centimeter equals 100 newtons. So all I'm doing now is just, I'm going to scoot the camera a little, is just drawing a scale drawing. Now I have my two other forces, and I kind of know what they're going to be because I know this has to be balanced, and I know these two are going to be equal and these two are going to be equal. Okay, so I can draw this player on sled, F normal ground on sled, and then I'm going to have the friction force, and that's the big unknown we have now, right? Which we can figure out just by inspection. But what if all the arrows didn't point in really nice, neat directions? Right? That's what the force addition diagram is going to do for us. So let's think about how we want to draw these force addition diagrams. If we think about one of the common vectors to think about a displacement vector, that is, if I start here and I walked to here, I would represent that trip with a vector like that, right? And let's say I then sort of turned a corner and I walked to here, and then my next displacement vector would be like that. So if I wanted to describe the whole walk, the entire thing, both legs, I would draw a vector that points like this, okay? So what that seems to suggest is if we want to add vectors together, we should put the tail of the second vector on the head of the first vector and then draw a resultant vector all the way to the end, okay? What if these vectors added up to 0? Let's say we took a walk up, let's see, northeast and then due east, and then we came back along this path, and we ended up right back where we started. Our displacement would be 0, and so when I add these three vectors up, they should result in a total vector of 0. So that's what a vector addition diagram for 0 total vector would look like. It would look like a closed shape. That is, the tip of this vector right here falls right on the tail of the very first vector you drew. So if I were to draw a vector from the tail of the first vector to the head of the last vector, it would be exactly 0 long, right? So I'm going to erase these, and we're going to see how we can add these 4 vectors over here. So let's draw the first one, and the one I always like to start with is the one I know the most about. So I'd either start with the normal force that the person's exerted on the sled, since that was given to us, or the gravitational force. And I'm just sort of in the habit of always starting with the gravitational force. You don't need to. But I'm not going to start with the forces that I have to deduce, right? So here's the gravitational force. And I made sure to draw it 2.5 centimeters long so that I'm obeying my scale, okay? And then the next vector I'm going to draw is going to be the vector that represents the push of the player on the sled. So I'm going to make that 1 centimeter long. And now look how careful I was to make sure that this vector was really at 90 degrees. In fact, I should probably be a little more careful. I should probably make a little mark here. Draw sort of a light thin line. See that? And then put a 1 centimeter vector right along that light thin pencil line. And then I can sort of erase the pencil line so it's clear where my vector is. So the reason I did that was to make sure there's really a 90-degree angle between these two vectors, as there should be, right? I can't change the direction of any of these vectors as I move them from this diagram to this diagram, okay? That's a really important, crucial point, and as soon as we start doing problems where the vectors point in various directions, like this problem that you're going to do, you're going to have some kind of force diagram that looks like this, okay? I'm not finished, right? But you're going to have something like that. These angles, this 20-degree angle here, it's going to be really crucial that you replicate that on the vector addition diagram and not just sort of eyeball it. You've got to use your protractor. You've got to use the protractor to measure angles and get distances and get the lengths of the vectors just right. Okay, so we know that now the normal force that the ground exerts on the sled is going to point directly up, so I'm going to make a little mark at 90 degrees so I know exactly what direction. Again, I'm going to draw a thin, long line. And right at first, so you could even make this a dotted line, right? Now right at first, I'm not quite sure how long this should be. Okay, we're pretending that it's not totally obvious here. So, but I do know that it has to go in this direction. The other thing I know is that this friction vector has to point in the horizontal directions. And I know one other thing. I know that these all add up to 0. So I know the tip of the friction vector has to point right to the tail of the very first vector I added. Okay? And it has to be horizontal. So it needs to be pointing along here. So now I look at where these two lines intersect. There's only one option for how long this vector could be and how long that vector could be that make all the vectors add up to 0. Okay? So now I have my diagram, and I didn't draw that very well. Please, you got to be careful and draw these actually exercise a lot of care to draw these just at the angles they're supposed to be. So here we go. F normal ground on sled, FG earth on sled, F normal player on sled, and F friction player, ground, not player, ground on sled. Okay? I can erase some of these extra lines. Okay, so this is a force addition diagram. Note that it's to scale. If we had not known how big these two vectors were, we can now measure them. We could say, oh, that normal 2.5 centimeters, it must be 250 newtons, and this one is, oh, it comes out to be 1 centimeter, it must be 100 newtons. Yeah, but we knew that already. But like I said, on more difficult diagrams like this, it's going to come in really handy to use a scale and to use your protractor to get the angles exactly right. Okay, so that's how we add up force vectors tail to head. And when we have a balanced situation, the figure that we make will close. That is, the head of the last vector we add will fall right on the tail of the first vector that we added. Okay, so good luck. Email me with questions if you need it. There's another video on my YouTube channel about replicating vectors at angles like this vector is going to be in this problem using your protractor. So just a few hints on how to use your protractor carefully. And that's it. Thank you.